All right, true confession. We had a little bit of a malfunction with the phone, but we're good now.
Yeah.
Okay, so notice how there is both a translational and rotational motion.
So there's a straight line that the string makes, and then this is going around and around and around.
Okay, so translational, mass falling straight down a straight line. Rotational.
The T is spinning.
What is the relation between translational and rotational motion?
Well, where is the change from one to the other? It happens right there.
So, didn't we have a Rosetta Stone to help us go from angular to that stripe?
It was an equation. That's the, what was it?
S equals R theta?
Yes, it is.
Okay, so we need to use that, and our stripe on the ground, just like Blake was showing,
Is now going to be the string. The string is the S. The R would have to do with a pipe, and the theta is this.
Okay, so what things could we measure here? And what can we calculate? Let's start with measure. So this is our apparatus. We could measure
the distance, the height that the thing fell.
go, 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 go.
Boom, boom. Here we're running it in reverse. See how we're winding up? So we could measure
And you'd want to measure from the bottom of right here, right?
to the ground.
Okay, to the ground. And what else can we measure as it goes from the top to the bottom?
Well, we could take a stopwatch and do on your mark, get set. How long does it take to fall? This one's slow. I'm getting bored already.
Yeah.
Okay.
Okay, and then you mentioned, Waken, that the radius was gonna have to do with the pipe, right?
Yeah, so we need to measure the diameter
So we could
of the pipe.
figure out how to measure the diameter here and work our magic, yes.
Yeah.
Okay, so keeping that in mind, now my other question is, what could we calculate?
Well,
Should we come back to this?
I think we should come back to that one.
Think about it.
Yeah.
What can we calculate? Okay, what are the kinematic equations for translational and rotational motion? Page 242. You guys should have these written down already. If you don't,
Well, they had that
down.
little matrix.
Oh yeah, for the homework. Right, so these are our equations.
These are the ones we did back in October.
Translational, rotational.
Here's the ones we just, and they're just parallel universes.
And this is a good question. What is Newton's second law for both? Should I write this on the board or should I just talk?
Yeah. Well, the second law is force net equals mass times acceleration.
And then what is the parallel universe for?
Well, force is going to be torque. Mass will be moment of inertia, and angular acceleration.
Now, aren't we trying to figure out what the moment of inertia is?
That was the challenge at the start.
So it looks like we have some players in the game that we're going to need.
Yeah.
What would you need to know in order to find the tension in the string as the mass falls?
Well, you'd need to know the acceleration of the mass.
So the force of tension is going to equal. So you said the acceleration of the mass?
Yeah. But how could we find the acceleration of the mass?
Oh, I see what you're saying.
So first we'd have to have the acceleration.
Yeah.
Well, the mass originally, its velocity would be 0. So we'd have the original velocity.
Original velocity is 0. Okay, and we have the delta y.
The height that it falls, the distance.
And we have the time.
We'd have the time,
We're
and we
trying to
could
find
find the
acceleration.
So which equation? What variable? Write down the variables we have.
We have initial velocity.
It's going to be 0.
We will have the time. We'll do it later.
Yeah.
And we will have the delta y. We are missing final velocity.
Which equation is missing final velocity from? I know it's upside down. Yeah. The original 1/2 at squared. And how would you? The original velocity is 0. Multiply both sides times 2. Divide by t squared. Boom, 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 boom.
Okay, so this is how we could find the acceleration. But what does that have to do with my force of tension?
Boys and girls, you got this written down? Because she's going to erase that right now.
Gonna erase it.
Yeah.
There we go. So you need to use.
So now you've got up there on the top, force equals mass times acceleration. And what are the, we'll put net force.
Oh yeah, sorry. No, right here, not here.
So we've got the E is equal to the force of gravity down. So that'd be the MA. No,
Oh, sorry, you want me
just,
to do
just
the whole?
keep what we got.
Yeah.
That MA is equal to the force of gravity down.
Plus,
The force of tension up.
I mean, check this out. If we want to know what the tension on the string is as it's falling right here, I mean, we've got two forces in play. We've got the force of gravity pulling it down, and then the force of tension pulling it up.
And when you let go,
oh, sorry, it's all tied up.
oh, it's
yeah, it's all tied up.
but it did it a minute ago, right?
Okay, yes.
So as it accelerates downward,
So,
how would you solve this for the force of tension?
well, I'm gonna go ahead and erase these that are here now. I do need to erase them. Okay, so for the force of tension, I'm gonna go ahead and subtract the force of gravity. So MA minus F of G equals F of T. And we know that this is going to be up. We know that this is going to be down.
So that's
and
subtracting a negative.
Yes, exactly.
Of course, the net force is also down. So that's going to be a negative
Yes.
minus a negative.
Now, what was the mass that we have there? Is it 200?
It's 200 grams.
200 grams or
0.2 kilograms.
How many newtons is that? You can multiply by the acceleration.
I think it's
Easy
going to be
stuff.
2 newtons. So, and we'd have the tension in the string as the mass falls.
Yeah. Oh, I'm
No, we
sorry.
don't need to calculate that
No,
right now.
It's not going to be 2 newtons. The acceleration's from our.
Right, the force of
yeah.
gravity will be 2 newtons.
Yeah, this is going to be 2 newtons. I'm sorry. Oh, yeah, I'm trying. Right here. Sorry.
So we haven't got the acceleration yet, but we can get that.
Yes.
All right, so let's go.
Moving right along here. What does the force of tension in the string contribute to the motion of the apparatus?
Well, it pulls, the string pulls right here and makes it go around. It
Like this, right?
yeah.
So this looks a lot like the bicycle wheel question that we asked you guys a while ago, right? We have this radius r, and the force of tension pulls. This is a tangential force right here.
Uh-huh. So it's a twisting force. And what do you call a twisting force?
A torque.
Torque equals
But what kind of force?
the tension. And the lever arm would be the radius.
Oh yeah.
No,
Radius.
L is good.
L equals r.
Yeah.
Okay. So our net torque equals the moment of inertia times the acceleration, and we are asking you to find the moment of inertia. Now, normally.
Okay, now let's go back to that slide. How could we find the angular acceleration? Because
Oh, yes, thank you.
the net force is going to be the torque, right? Just like we found there. Now we need to find the moment, I beg your pardon, the angular acceleration. So,
Ultimately,
going back to these equations right here.
ultimately, this is what we're trying to find, right? And we just talked about how to find the net torque.
Yeah.
But how do we find this still?
Well, we have to have the kinematic equations for
do.
rotational motion, for angular motion. So, what variables do we have?
Well, we have the what do we have?
Original angular velocity
We have the original angle. Oh yeah, we have it, which is 0,
is 0. We've got the time.
which is whatever we get. Oh, and we've got the display. Oh, we'll talk about the displacement.
Oh, wait a minute. We do.
We do.
We have the angular display. We can find the angular displacement.
Okay, how do we do that? Well, we can't just measure it straight down.
S
like we did
equals
down
r
to y.
theta. So the change in theta will be S over R. And S is the string.
Yeah,
Is a stripe, but it's going to be the string.
divided by, what was our radius? Well, whatever our radius is.
Yeah.
Okay, we've got time. Oh, and then we're trying to find acceleration.
Yeah.
Whatever we get for our time, we'll write that in there.
So we want the acceleration. There's no angular velocity final. That sounds like Vought.
Except for it's what? This goes away.
And erase that other stuff so it's clear.
Oh, sorry.
No.
I know I should have erased it all before.
It's cool.
Just erase, rid of all of it over here.
So now it looks a lot like what we did a minute ago, except
Yeah.
for angular motion.
Right there, like that, right?
Yeah. You guys follow what just happened?
So,
Now it's time to do the lab.
okay, here we go. Like we said, like we were gonna say, normally you guys would be doing this. We'd have a timer and a winder. Clearly, the winder is very important.
Yeah, that's right.
The research sheet, recorder, and calculations checker, but we will have to come back to this.
Go ahead and open the door, see who it is. This had better be good.
Oh, let me put my mask on.
You still work
It's
here?
Mr. Sergeant.
What's up, Mr. Sergeant? Sorry, I couldn't see who it was.
Sorry, I didn't know. I knew I was totally interrupting. But
Watch what you're watch what
You
we're
could
gonna
be a
do.
star in our show.
Okay.
First of all,
I
yeah.
feel bad if I'm interrupting the video, but I will watch.
Okay,
All right.
so Mr. Sergeant is our guest.
Oh.
Conduct an investigation to find the moment of inertia. Okay.
So
Actually, Mr. Sergeant, would you help us?
Yes.
Okay, great.
first we need to measure the diameter of the pipe.
Okay, let's do that first. Oh, reset. Okay, so
Do you need to use pi for that, Mr. Boykin?
No.
we're gonna cheat and use
Okay.
it.
I see. You don't. Use calipers.
Okay.
Well, actually, what we're doing here is the relation between angular motion and linear motion. And that's S equals R theta. S is the string. R is the radius of the pipe. She just measured the diameter, and the diameter of the pipe is
2.51 centimeters.
2.5. Let's just call it 2.5.
2.50. That's a zero. Boop, boop.
So the radius is half of that.
Is that right? One,
Yeah.
2. There we go. Okay. Oh, and that's and the radius is half of that.
So it's 0.0125
0, 1, 2,
is the radius.
Boom.
Okay.
Wait, what else do we have to find?
We need to measure the height.
Oh, I haven't done this part yet.
So, Mr. Sergeant, would you hold the pipe so it doesn't turn?
Yes, I will walk in front of the
Otherwise-
camera and then.
Otherwise, I'm gonna whack myself in the face. Okay. And give me a little slack there. Right there, Mr. Boykin?
Yeah, now measure the
that
distance
protocol?
from the floor to the bottom of the
It's actually really good that you're here. Okay, so I'm gonna call that 0.73 meters.
0.73 meters. Okay, so the height, I want to write this on the board. This is delta y is 0.73 meters. Okay, so
I'm gonna have
we need to
Mr.
find out
Sergeant-
how much time it takes to fall.
Okay, let me just practice using this thing because I always mess it up. Okay, all right, on your marks, get set, go. Dun, 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 dun. I'm just gonna look at the floor. Dun, 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 dun. Dun, 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 dun.
Boom!
Okay, got it. Okay.
How much
All right,
time?
Mr. Sergeant, you have been very helpful. Happy Friday, and I'll swing by you later. and talk to
Okay.
you.
Thank you very much.
What do we? A round of applause for Mr. Sergeant.
Yay!
Okay, 16.44 seconds.
So the time is 16.44 seconds. So boys and girls, here's our data. Now, find the moment of inertia
Oh, is this last slide
for
right
the
here?
apparatus. I don't know what's next.
Oh yeah, no, that's
Yep.
not slide. Okay, so now conduct your event. Well, we already conducted the investigation. Figure out what Mr. Wilkin just said. Find the moment of inertia. We just looked through your notes. We just walked you through exactly how to do it.
So do it.
Do it.